Okay, Morgan, let's try this session, something I've never done before, which is give a tutoring session without the student on the other end. I'll give it a shot though. This first problem is rather unusual, mainly because we're not dealing with a function. Here, let me get my thing in drawing mode so that I can write. If we start this problem by drawing the points, we don't know what the function is, but we know we've got these 5 data points. Well, there's 10, we'll call that minus 13. And then when x is 14, y is minus 7. And when x is 18, y is minus 1. And when x is 22, y is plus 2. When x is 26, y is 3. And when x is 30, y is 7. So that's 30 on the x-axis. This is f of x. Now, they only want the area from 10 to 30. And they want the lower estimate and they want the upper estimate. Well, this is a little tricky. Typically, if we have a function, if I go over here in red, and I have a function that's always increasing, well, left-hand endpoints underestimate it, right-hand endpoints overestimate it. Okay? So that's what I'm going to do in this function. I'm going to use left-hand endpoints and right-hand endpoints. So the lower estimate I'm going to do in red. Well, there's the left-hand endpoint of that triangle, the only one, not triangle, rectangle. There's the left-hand endpoint of that one. This one's a little tricky. It's that rectangle and it's that rectangle. And this one would be that rectangle. And the last one would be this rectangle. Sorry, I'm a little off there, but I think for explanation purposes, it works. Now, if, in yellow, I'm going to kind of graph what that function might look like if it were continuous. Okay? And it looks like above the x-axis that my red rectangles are the lower estimate, right? But below the x-axis, at first glance, it looks like it's overestimating it. In other words, when the f of x values are in negative territory, it appears that left-hand endpoints overestimate it. But on second glance, they really do not overestimate it. They underestimate it. In other words, this is a negative area. So the actual negative area that we get is a negative number, and the area of the red rectangle is going to be a lower negative number. So in reality, it really is underestimating it when we do left-hand endpoints. As long as the function is always increasing, then left-hand endpoints underestimate it, and right-hand endpoints overestimate it. So let's figure out what our lower estimate of this area is. And remember, all area is negative if it's below the x-axis. So this first one is 4 units wide and 13 units deep. That's minus 52. Okay, that's that first rectangle. Second rectangle goes from 14 to 18, so it's also 4 units wide, and it's 7 units deep. That means that's minus 28. The third rectangle, which is 2 different rectangles, but the third one is 4 units wide, 1 unit, still negative, that's minus 4. This one, 4 units wide, positive 2, that's plus 8. This one's 4 units wide, 3, that's 12. This one is 4 units wide, 7 high, that's plus 28. So if we add up all of those numbers, we get the 28s cancel. We get minus 56 and plus 20. So the red is minus 36. And it's okay to have a negative area. The area under the curve, anything under the x-axis is negative. Okay? Now let's see if in black I can do the upper estimate. Well, the upper estimate uses right-hand endpoint. Let's see. First of all, I got that dot in the wrong spot. Let me put it there. Well, if I look at my yellow curve, my first rectangle is going to be that one. In other words, there's the right-hand endpoint that intersects with the yellow curve, or in fact the only data point. And then that one is that one. This one overestimates above the x-axis. Remember, I'm using right-hand endpoints now. And that one's at 7. I feel like I left out a triangle here. That was 10 to 14, 14 to 18, 18 to 22, 22 to 26, 26 to 30. Okay, we're correct here. That's the last rectangle. All right, now let's figure out what our upper estimate is. It's the area of these rectangles. Well, that one's 7 times 4, but it's still in negative territory, so that's negative 28. This one is 1 times 4, so that's negative 4. This one's in positive territory. That's 2 times 4, so that's 8. This one is 4 times 3, that's 12. And this one is 4 times 7, that's plus 28. Now the 28s again cancel, but now I got a net of 16. So that is your upper estimate, and that is your lower estimate. And this is a very difficult conceptual problem because it's not a continuous function. But the secret really is to connect those dots and make it a continuous function, and then use the way you would normally do left-hand and right-hand endpoints. It's just confusing below the x-axis because it looks like left-hand endpoints overestimates it, but it really doesn't. It underestimates it when you think about the fact that you're dealing with a negative number. All right. to the next problem. This is not really as hard. They want you to evaluate each integral by interpreting it in terms of area, knowing that the area under the curve is the same as the integral. So if they want to go from 0 to 12, they're talking about the area of that. Well, I can break that down into let's see, this must be 18. That must be 6. I can do this as trapezoids or rectangles. Trapezoids is really the best way to do it. For one thing, you want to get in the habit of doing trapezoids. Okay? So, first of all, what's the area of A? Well, it's base 1, which is 18, plus base 2, which is 6, divided by 2, times its thickness or height. Only remember, we're looking at trapezoids that are on their sides. So the thickness, which is 12, is really what you would normally call the height of a trapezoid. And that's 12 times 12, so that's 144. We don't need calculus for that. We can use geometry, which is what I used to figure the area of that trapezoid. Now, the area from 0 to 30, I got to add in this area to my first area. Well, what's this area? That's a trapezoid also, but it's more easily figured if I treat it as a triangle. No, it isn't. No, I can treat it as a trapezoid. One base is 6 units, the other base is 18. So it's 18 plus 6 divided by 2 times its thickness, which is 18. So that is 12 times 18, which is 212. 12 times 18, no, 216. Yeah, 216. So that area, in fact, the better way to label this is, let's make this 144. Let's make this 216, which makes the area from 0 to 30 the sum of those two numbers, which is 360. Now, from 30 to 42, there's 42. That's this area here. The only thing we know about it is it's going to be a negative number. But it's that triangle. And that triangle goes 12 units wide, 18 units deep, so it's 12 times 18 divided by 2. That's 9 times 12, that's 108, but it's negative 108. Negative 108. So that is negative 108. And now the last part of this question is 0 to 54. Well, there's 54. And we got to figure out the area of this last trapezoid. Well, again, one base is 12. The other base is 18. Our average base is 15. Multiplying it by the thickness of 6. no, 12, excuse me. That thing is 180, but it's minus 180. So to get the total area from 0 to 54, I'm going to add these two positives and add it to these two negatives. Well, that gives me 360 minus 288, or a net 72. That's what the answer is 72 square something, square units. And that looks about right. In other words, if I erase everything and I compare this area, which is positive, with this area, which is negative, looks to me like the positive area is bigger, and indeed that's what our calculations told us, was that it was 72 units bigger. All right. I think that covers those two problems, Morgan. I will stop this.